here's the requested for a video on synthesis. You might have noticed in homework set 13, there's these really great series of synthesis problems. That's problem number 59 from the Klein textbook. I thought I might just give sort of a commentary, sort of the thought process that you should have in looking at these problems. Because again, the answers don't matter, because if you're trying to memorize these answers, you will never get anything right on the exam. You'll just jot down, scribble down something that like you vaguely remember. And I could never learn organic chemistry that way, because I promise you I cannot remember any of these things. I can figure them out, but I cannot remember these. So here's the thought process. Since we're already looking at the answer key for this, try not to think, look at the answers, I suppose, but let's see. Okay, so the first one, here's our products. That's the target that we want to look at. And the main thing I want you to get a good handle on is to get to be able to make observations about the target molecule, the target product that will help you design your synthesis. So let's make observations about this molecule here. First, there's an alcohol that would be at this carbon, and then there's a new carbon added, right? So that's when I realized that I probably should, if I have some sort of a Grignard reagent, or like something like a methyl Grignard, that would open the epoxide at the less hindered site, and that would give us essentially the skeleton and the product here after this alcohol product here after the acid workup. So that's the thought process there. The second problem is very similar. You have this ketone, but the ketone is at the same carbon that we had the alcohol as the previous problem, and then we're starting with the same study material. So what I literally did is I just copied and pasted the same answer here as the top, and then oxidize the secondary alcohol to the ketone. So to be thinking backwards though, I know that ketone can be produced by a secondary alcohol, so that's the thinking backward piece, okay? The next question, we have a chloride in the end of this chain, and then we also notice that there is 2 carbons that are added here. So there might be a dissection here at this point, because we're only starting with 3 carbons in the beginning, right? Now the chloride, we know that we can make that from alcohol with using like HCl or thionyl chloride. In this case, this is thionyl chloride. So that's what I chose to do there. There's other ways to do it. You can make a tosylate and then add sodium chloride and use chloride as the nucleophile. Many different ways to do this, but here's one way to do it with thionyl chloride from primary alcohol. And to make primary alcohol and add these 2 carbons at the same time, I can definitely use this epoxide. So that's what I did there. Okay, same idea as the earlier. So the idea here is that we're going to have this Grignard that will open the epoxide like so. Okay, so that's the mechanistic idea. Okay, now this, well, I should say that was the idea for here, but the same the next problem is kind of similar. The only difference is we have chloride on the same carbon, but there's an extra carbon added. So what I did is I went to the same alcohol as before, but then I oxidized. If I were to oxidize that to the aldehyde, I can add the methyl grignard. So here the idea here, of course, is this type of a reaction. That'll give us alkoxide after acid workup. That'll give us a secondary alcohol, which can be displaced or replaced by chloride using thionyl chloride reaction here. So that's what I did there. Okay. Now this target ether, that's an ether, right? So we should be able to make that through Williamson ether synthesis method. And we can dissect this either here or there, but one of those is utterly impossible. We cannot dissect it here because then we would have to do, remember Williamson ether synthesis is an SN2 reaction. You cannot do an SN2 reaction on a tertiary carbon. So for that reason, we're going to dissect it right here. And that will get us back to the terbutanol. Okay. So the idea here, of course, is that if we had this T-butoxide, alkoxide, that could do this SN2, even though it's a little bit bulkier than nucleophile. But the other way around would not be possible. F here is very similar to the earlier idea. We're just, again, simply open an epoxide with this alkoxide, like so. Okay. And then G here is, again, that's an ether. We was thinking about Williamson ether synthesis. And to do that, we can again dissect this at a couple of different points, but only one of them would be feasible, right? Well, I guess both of these could be potentially feasible, but excuse me, we could dissect it there, and that's fine. I just happen to dissect it at the other position here. Actually, mainly so that we eliminate the possibility of like a competing E2 reactions, but that doesn't really matter that much for this problem. So for this problem, I can see a number of different ways to do this. But again, the key idea here was Williamson ether synthesis. And then I had to introduce leaving group at the end, so that's an anti-Markovnikov reaction that is done through a radical process with a peroxide, as you recall. And then the easiest way to make this ether, where the double bond is, in a Markovnikov fashion, would be oxymercuration reaction, except we're using alcohol as the solvent, so that's technically alkoxy mercuration reaction followed by reduction. Okay. Now, this next problem, we're trying to make this epoxide from this alkyne. One of the observations, the number of carbons does not change, but and then we have the new functional group, the epoxide, right? One way to introduce that is epoxidation of alkene. So I propose to have an alkene. Remember, synthesis problem, you want to think backwards from the product, right? The target. The first thing I'm thinking about is this alkene, and then that can be produced by hydrogenation of the alkyne from here. Okay? And then the next problem, here's the epoxide product, which can be formed through, again, an epoxidation reaction. Might as well, we could use MCPBA, the same reagent. We notice the stereochemistry here is cis, so the starting material must have been cis. And to make the cis alkene from alkyne, we need to do Lindlar's catalyst hydrogenation. So here's the Landler's catalyst. Okay, that's the poisoned palladium catalyst. The next problem, we have a trans epoxide stereochemistry. So that must be from a trans double bond, which you can make that through a radical anion reduction using sodium in liquid ammonia from alkyne. So that's that idea. Okay. The next problem here, we are adding a couple of carbons here, right? And then we are also introducing this alcohol. So remember, if you have to introduce a couple, some number of carbons, and at the same time introduce an alcohol, one of the great ways to do it is epoxide opening. We've seen that in a number of these problems, right? So if we have this epoxide, and if we have a ethyl Grignard, that will open the epoxide ring right here, and after the acid workup we get to the desired product. So that's the idea here. And this next problem, it's kind of a tricky one. We're going from the methoxybenzene to ethoxybenzene. So how do you do that? You can't just add a carbon, I just want you to know, because this carbon is not at all reactive per se. You can't there's no way to just add a carbon to a methyl group. Okay, you would have to replace a hydrogen and add a carbon. That there's not any standard chemistry that you can do to make that happen. So what you could do is you could make this ethyl phenyl ether from a phenyl alcohol like this through Williamson ether synthesis method here, SN2 reaction, and we should be able to make this alcohol phenol from the methoxy starting material if we break that ether up. Ether cleavage is possible under strongly acidic condition. Please take a look at the notes there, right? That's possible, so we did that. The next problem, this is our target. It's hard to see, sorry, but there's a primary alcohol in the end chain there. Again, we see some evidence that there's a couple of carbons added here, right? And then we're making an alcohol, so then naturally it's a good idea to do an epoxide opening or oxyring opening, which we could do by having this carbon nucleophilic. The only way that you guys know to make a carbon nucleophilic is to make Grignard reagent. So you could do that from a halogenated material. So here's an iodocyclohexane as an example, and that can be synthesized by cleaving this ether under strongly acidic condition using hydrogen iodide. Okay. Next problem here, we have this product here, and we seem to be adding again these two carbons, and we're forming that alcohol again. For whatever reason, Klein likes epoxide opening, and especially this problem 59 seems to be one of the main purposes of it, is to like drive this idea into our minds about like, if you use an epoxide, you can add a couple carbons and introduce an alcohol all at the same time. So this is going to be our nucleophile, and that's not going to be an issue because you can easily make an alkoxide from the corresponding alcohol there using a strong base. Our next problem, once again, we're adding two carbons in an alcohol. We can achieve that with an epoxide opening. One of the only ways we know to turn a carbon into a nucleophile, once again, is to make a Grignard reagent. So that's the condition to make a Grignard reagent. Okay. Well, this problem Q, the target, of course, is this aldehyde. aldehyde. How many ways do we know to make aldehyde? You could do ozonolysis, maybe not likely because that loses carbons. And we could do it by hydroboration and oxidation of an alkyne, or we could do it by oxidizing of an alcohol. And if you do the latter, right, like we would be able to make this aldehyde from that primary alcohol. And then if we pay attention to that primary alcohol, we'll notice that we would have to add a couple of carbons, again, epoxide opening. For R, this also seems to be an epoxide opening situation because we have this situation, except one thing we need to be careful about is the epoxide seems to be opening at the more substituted site. Remember, that only happens under acidic condition when the epoxide is positively charged, and that's why we have the acidic condition here, okay? In this product, in S, the alkoxide seems to be adding or opening the epoxide at the less hindered carbon, so this carbon. That would have only happen under basic condition followed by acidic workup to protonate. So that's why we have basic condition to make an alkoxide. Okay. And these last couple of problems just have to do with making certain epoxides. This epoxide can be formed from this cyclohexene, which can be formed by elimination of a leaving group like a bromide, which can be introduced to the starting material alkane, especially if it's at the most substituted carbon. You can do that with radical bromination. So that's that. Now, if we have access to this epoxide, you can open that under basic condition to produce the product here. Now, how do I know that this requires a basic condition and not acidic condition? Well, because look here, here's the nucleophile that must have opened the epoxide, the methoxide, right? The nucleophile is added at the less hindered carbon, right? So that happens under basic condition. If it was the other way around, if it opened at the more substituted carbon, that would happen under acidic condition. So hopefully this